My name is Shayne Miel, and my paper is Looking for Low-Proficiency Sentences in English Language Learner Writing. The task is to provide automated feedback to ELL writers on areas of low proficiency in their writing. Previous work is focused on grammatical error detection and correction. However, that is not enough because some sentences are too jumbled to find specific errors, and some sentences sound unnatural even with no actual errors. It's also extremely hard to get right. In the 2014 Connell shared task on grammatical error correction, the best paper only got an F score of 37.3. Recent work has boosted that by 10 points, but there is a ceiling because human agreement is really low. It is hard to get people to agree on what errors exist in any given sentence. I'm trying a different approach by asking what areas of the writing look the least like native English writing. I've collected a large data set of native and non-native English writing and have trained a convolutional network to predict, at the document level, whether the writing is from an English language learner. My hypothesis is that I can use the window probabilities, that is the output of the convolution before the pooling layer, to highlight areas of the text that could use revision. The data was collected from 13 smaller data sets, spanning many countries and native languages, and it contains approximately equal numbers of native and non-native English writing. I cleaned the data to remove any potential confounds caused by formatting issues, and split the train, dev, and test sets by subcorpus to avoid learning specifics about the corpora. After cleaning, I was left with 77,000 essays written by students with 25 different native languages. Let's talk about my models. DeepFilter is a convolutional neural network that uses a deep network as its convolutional filter. The inputs are sliding windows of character embeddings. The convolutional filter is a bidirectional LSTM where the final hidden state is fed through a fully connected layer to a sigmoid activation. This gives the probability that each overlapping window of text was written by an ELL writer. These probabilities are sent into a mean or max pooling over time layer to get a document level probability. I minimize the log loss between these predictions and whether the essay was actually written by an ELL student. Dropout is applied on the way into and the way out of the convolutional layer. I also use another model, which I'm calling prompt aware. It adds a secondary output and loss to the deep filter network. This approach was described in Zhang and Edinger's Enlightening Deep Neural Networks with Knowledge of Confounding Factors. Starting from the hidden layer of the LSTM, I use a new fully connected layer to predict which of the 95 prompts in the training set the essay was written to. The cross-entropy loss of this prediction is then added to the existing log loss. This essentially regularizes the hidden layer so that the network can generalize more easily, and is intuitively similar to regressing out a confound in linear regression. My baseline is a logistic regression, sort of. It uses the same convolutional structure as DeepFilter, but the input layer is a sparse feature vector of character foregrounds for each window of text. The convolutional filter is a single fully connected layer plus a sigmoid activation. I use area under the ROC curve between the document level predictions and whether the essay was written by an ELL student as the early stopping criteria and as the document level model evaluation. In addition, I hand annotated 200 randomly sampled windows from the test set with a 1 if I would give the student feedback on that window and a 0 otherwise. The area under the curve with these labels and the window level probabilities provides a second model evaluation metric. All three models are tried with both mean and max pooling over time. Hyperparameters were held constant across models. As you can see, DeepFilter with mean pooling does significantly better than the baseline at predicting the document level classification. However, the prompt-aware model with max pooling edges it out on the window level task, although none of them do very well on this small random sample. Looking at the essays that DeepFilter predicted as being very likely ELL writing, you see a lot of low proficiency sections like internet can use sometime and somewhere, or add to city have lots of Wi-Fi spot. However, when we turn our attention to a sampling of the highest probability windows, according to the prompt-aware max model, we can see why the window level prediction quality may not be so good. One thing that jumps out at me is the large number of transitional phrases that are being captured. We have heard from our school partners that it is very common for ELL students to be taught to use these standard phrases to enhance the cohesion of their essays, and they tend to use them more often than native writers. In other sentences, however, you can see evidence of the kinds of writing that I intended for this model to flag. The good news is that DeepFilter is able to significantly outperform the baseline at classifying native versus non-native English writing. The bad news is that my hypothesis that I could use the window level probabilities to find areas of low proficiency may not hold up. It makes sense that ELL students who are struggling to communicate would tend to lean on things like transitional devices, and that the model would be able to pick up on that pattern more easily than learning the myriad ways a student might introduce an error into a sentence. Some next steps are trying to use a language model trained on well-edited English and see if perplexity is related to proficiency. I will also collect more annotations. Thank you for watching my presentation. Please feel free to email me with any questions.